All right, so now that we've looked at the three different surfaces of the Earth that we use to model the entire shape of the Earth, so we've got the actual Earth model, we've got the geoid, and we've got the ellipsoid, let's look at the impact of the effects of the Earth mass and gravity on our geodetic observations. Now, because of the going through from the start of this lecture, we did mention that the reason geodetic surveying is quite complex is because it takes the physical properties of the Earth into account when we are dealing with observations. Obviously, because the Earth is always moving, because it's covered by land masses, it's actually affected by a lot of physical things that impacts how we carry out our jobs. So we're just saying that there are complexities when it comes to geodetic surveys, because one of them being because the Earth's mass and gravity impacts the overall model of the Earth. Okay, because Earth has mass and Earth has a center of mass, and masses exert gravitational attraction. The forces of those gravitational attraction is related to a distance from a point to the center of the Earth, meaning that at every point on the Earth, the center of gravity will be different because of the terrain, because of obviously how far we are from the center of mass. So think of it this way: if we are traveling up on higher terrain, up a mountain, gravity will obviously be lower than if we're, say, on a flat surface. So the closer you are to the center of mass, the higher the gravity, and as you go up, it does reduce. And then to add to that complexity, we also have the oceans, which have the surface of the oceans are always deforming because of a number of effects. So things like tides, currents, weather conditions, etc. They also change the behavior of oceans, and compounding that with the effects of gravity, we do need to then consider what might be the best model to use. This is where the term geoid comes in. So this is not geodesy. My apologies there, made a mistake, but yeah, this slide should say the geoid. So the geoid is a model of the Earth that a surface of equal gravity that can be used to approximate the Earth's surface is represented as a geoid, and I'll explain that in a minute again. I know it can be a bit confusing. So a geoid is the shape that the ocean would take under the influence of gravity and the rotation of the Earth. Okay, so if we were to assume that the oceans are permeated around the land masses, so we take the land masses out of the equation, and we also remove the effects of tides and currents, the shape of that ocean, the shape that the ocean would take under that influence of gravity and the rotation of the Earth would create this shape of the geoid, or the model of the geoid. So the geoid approximates the Earth's surface through equal gravity on the surface of the Earth as sea level permeates through land masses. So that shape that we end up with, which is the geoid, assuming that the gravity is equal all around, and we're taking the rotation of the Earth into account, we're removing tides, we're removing currents, we're left with this shape that is quite undulating. So it's not smooth, it's quite, as you see, it's quite unpredictable in shape. And the issue with having a shape like that is that we can't actually use it to give us a easy representation of the surface of the Earth, because it's obviously quite a complex shape. So we can't model it mathematically. So as an irregular figure, it's very complicated to represent mathematically. So we need to come up with a way that we can best fit the Earth's shape, but in a way that's easy for us to work with. And this is where the spheroid or the ellipsoid comes in. So just remember that the spheroid is actually the same as the ellipsoid. The ellipsoid is defined as an ellipse that we rotate around its minor axis. Okay, so remember how I said that the surface, the Earth shape is not a perfect ellipse or a sphere. It's actually squished from the north to south direction. And reason being, again, okay, the north to south direction, it's a bit squished this way. Reason being that the distance along the equator is slightly longer than the north to south direction. And when we take that ellipse and we rotate it around its minor axis, then we have a ellipsoid, so that shape of an ellipsoid. So the reference ellipsoid is typically idealized representation of a physical Earth, meaning that we are taking the shape of the geoid that is not easy to represent mathematically, and we're giving it a much easier way of representing that shape so that we can define it mathematically, and then we can use it to better make sense of what we have when we're observing on the surface of the Earth, obviously. So with the ellipsoid, an ellipsoid is always defined by a minimum of 2 parameters. So I've already introduced you to this idea of having a distance going from the north to south direction that is shorter or smaller in length than the equator distance. And because of that, the line along the equator, we call that the semi-major axis. Okay, so that's, think of it as major, as in larger. And then we have the distance along the north to south direction, that would be our semi-minor axis, so this distance B. So as you can see, A and B are examples of a radius, but the two radii would be quite different because they're not actually the same length, one being longer than the other. And then the last one, the last parameter that we can use to define the ellipsoid is the flattening. And I'll show you what the flattening is in the next slide. But it's basically a formula that allows us to establish a relationship of how much flattening there is based on the semi-major axis and semi-minor axis. So you can have a combination of 3, but you need a minimum of 2 parameters to be able to define the ellipsoid. And once you know these 2 parameters, then you can do a wide range of computations that are related to the observations that you're taking on the surface of the ellipsoid. So geodetic reference systems, they need to have a few properties, and one being that they must be very well defined and accurate. And you can kind of think about why do we need that level of accuracy and having a well-defined reference system? Because a lot of times geodetic reference systems represent satellite motion. They also allow us to model Earth observations, so anything to do with mapping the surface of the Earth, studying crustal deformations, studying the relationships between the Earth and other celestial bodies, and then also it allows us to represent and analyze observations.